Geology isn't just pretty scenery. It's the slow force that builds, breaks, and reshapes the Earth. And every so often it leaves behind a place so strange it feels like the planet is showing you how it works. That is why a glacier can turn hollow at Skaftafell Ice Cave, a blue chamber carved from within the ice, forcing one question: what kind of force can shape solid, frozen mass from the inside out? And if the planet can carve ice into emptiness, it can also feed fire. The Darvaza gas crater has been burning for more than 50 years. So what keeps that flame alive? And what does it reveal about what's trapped beneath the ground? Then heat takes over at Grand Prismatic Spring, where the water bursts into impossible color. So why does this one pool glow like that? And what turns heat into a spectrum you can actually see? These aren't isolated wonders. They're clues, because Earth is full of hidden places where the surface is only the final layer, and the real story sits underneath in pressure, temperature, gas, ice, and time. In this video, we're going to peel those layers back one by one, so you don't just watch something unreal, you understand what built it, how it works, and why the planet only shows it for a moment. Darvaza gas crater. What does it mean when the ground can keep burning for more than 50 years? As if the desert has been left with an open furnace that never quite runs out? The Darvaza gas crater in Turkmenistan's Karakum Desert, often nicknamed the door to hell, is that kind of unsettling clue, because the fire is not coming from magma, but from fuel trapped underground. Most accounts trace it to a Soviet-era drilling accident in 1971, when the ground collapsed into a gas pocket and the site was ignited to stop gas from spreading. From that point on, the mechanism is brutally simple. Natural gas continues seeping up through the broken ground, and the open crater supplies the oxygen needed to keep the flame alive. That is why the fire behaves less like a single blaze and more like a field of shifting vents, bright patches that appear, weaken, and reappear as the underground flow finds new paths. The real hidden story is invisible. The desert floor is acting like a lid that cracked, and what looks like a spectacle is actually the surface signature of gas pressure and geology underneath. In recent years, Turkmenistan has publicly described efforts to reduce the crater's burning by drilling wells around it to capture methane. And independent satellite tracking has reported a significant drop in emissions and combustion. That shift matters because it reframes the crater from eternal fire to measurable system, a flame that rises and falls with supply, capture, and the changing routes gas takes underground. It also carries a larger lesson with real-world stakes. Every persistent burn like this is a reminder that what is trapped beneath the surface can escape quietly for years unless it is understood and managed. And as a geological clue, Darvaza points to the theme of the whole video. Earth hides its strongest forces below ground. Then, in rare places, it lets heat and gas write the evidence in plain sight. Why does a small lake keep a vivid pink color so steadily that, from above, it can look less like water and more like a deliberate mark on the landscape? That question leads straight to Lake Hillier on Middle Island in Western Australia's Recherche archipelago, where the setting itself is built for separation and stability. A long, narrow band of sand and dunes sits between the lake and the Southern Ocean, and that natural barrier helps the lake behave like a contained system rather than open coastal water. Inside that frame, the lake is only about 2,000 feet long and about 820 feet wide, yet the color is strong enough to overpower its small size. The barrier matters because it supports an extremely salty environment, and the salt crust around the shoreline hints that the chemistry here is intense and persistent. In water like this, salt-loving microorganisms can thrive, and sources commonly point to algae such as Dunaliella salina alongside red, salt-tolerant bacteria as part of what produces the pink tone. What makes the effect feel even more locked in is that descriptions note the pink color remains even when water is taken out in a container, suggesting the pigment is carried with the brine itself. Even so, the intensity is not permanent in the way paint is, because heavy rainfall can dilute salinity and soften the color until the lake returns to its more concentrated state. And because the area sits within the Recherche Archipelago Nature Reserve, direct access is limited. So many people experience the lake from scenic flights rather than as a casual shoreline stop. So the answer to the opening question is a layered mechanism. Isolation and geology create the extreme salt conditions. Microscopic life supplies protective pigments, and the lake holds that chemistry in place long enough for color to become its most visible signature. Grand Prismatic Spring. Why does one hot spring look like it's glowing in layers of color, as if heat itself has been turned into a spectrum you can see? Grand Prismatic Spring in Yellowstone's Midway Geyser Basin makes that question unavoidable, measuring about 370 feet across and more than 121 feet deep. That scale is sustained by Yellowstone's hydrothermal system, where groundwater circulates down, is heated at depth, and returns through natural fractures that act like hidden plumbing. At the center, temperatures remain high enough that very little can live there, which is why the pool stays a deep, clear blue instead of looking painted. As the hot water spreads outward and cools, life begins to take hold in the runoff, with heat-loving microorganisms forming thick mats along the margins. Those mats create the colors because different communities prefer different temperature ranges, so each ring becomes a boundary where one group gives way to another. That is why the outer bands shift through greens, yellows, and oranges over time. It is biology responding to heat and chemistry, not dye floating on the surface. Steam, wind, and changing light can soften or sharpen the spectrum, making the spring look like it's changing, even though the underlying process stays consistent. The same heat that produces the beauty also brings real risk. Yellowstone warns that ground around hot springs can be thin and fragile with scalding water beneath, which is why staying on boardwalks is non-negotiable. So the answer is a partnership. Geology delivers the heat and water, and living mats translate that invisible temperature gradient into color that the surface can't hide. Pamukkale is a white cascade of terraces and shallow basins that looks like snow on a warm hillside, even though it is being built by mineral water, not weather. It sits above the plain near the ancient site of Hierapolis in southwestern Turkey, where spring water emerges loaded with dissolved minerals and immediately starts changing the surface. The mechanism begins underground. Hot water dissolves calcium-rich material, then rises to the open air where it can finally release what it was holding. As the water reaches the surface, carbon dioxide escapes, and the water can no longer keep the calcium in solution. So calcite begins to deposit along every rim and lip it flows over. Those deposits start soft and fresh, then harden into travertine, gradually building the bright steps and natural walls that shape each pool like a shallow bowl. The terraces keep their clean, white look only when thin sheets of water continue to run, because flowing water spreads new mineral film while still feeding the next basin below. That is why the scene can feel temporary and revealed, not permanent. Small changes in water routing and season can shift which pools fill, which rims grow, and which surfaces dry out. Even the warmth is part of the clue, since geothermal outlet temperatures in the area are often described around 95 degrees Fahrenheit, keeping mineral-rich water active as it moves across the slope. Official heritage descriptions frame the landscape as calcite-laden waters creating terraced basins and petrified cascades, which is a formal way of saying the rock is still being manufactured in real time. In the end, Pamukkale is hidden geology made easy to read. Heat brings the water up, chemistry turns it into stone, and time stacks the result into a terrace system that keeps rewriting itself. Cappadocia is a landscape where soft volcanic rock has been carved into ridges, cones, and corridors so cleanly that the terrain can feel more like architecture than nature. Its foundation began with volcanic eruptions that spread ash and debris across the region, which later hardened into a softer rock layer that could be shaped far more easily than ordinary stone. Over long spans of time, wind and rain kept removing the weaker material, cutting valleys and exposing layers that had been buried in quiet for ages. Out of that steady removal came the fairy chimneys, rock spires that can reach about 130 feet tall, often protected by harder capstones that slow erosion at the top, while the softer rock wears away below. That same softness is also the human story, because rock that can be worn by weather can also be carved by hand, which is why cave rooms, chapels, and entire clusters of dwellings could be cut directly into the cliffs. And as the surface was being sculpted, the underground became another layer of adaptation, with hidden spaces excavated into the volcanic rock as places to store, shelter, and endure harsh moments. What makes the geology feel secret is that the shape is only the final layer of the story, while the real cause is buried in how volcanic deposits respond to erosion, cracking, and time. Even the color and contrast tend to sharpen with angle and shadow, so the same ridge can look ordinary at noon and suddenly patterned when the light turns low. The Garema rock sites were placed on the World Heritage List in 1985, a formal recognition that this terrain is not only unusual to see, but unusually informative about how it formed and how people live with it. In the end, Cappadocia reads like a complete sequence in one frame. Fire lays down the raw material. Air and water carve it into forms that look designed. and human life settles into the shapes the planet leaves behind. Zhangye Dangxia landform. How can a set of hills look like someone painted the earth in stripes and still be nothing more than stone, wind, and time doing ordinary work? The answer is Zhangye Dangxia landform in Gansu, China, protected inside a geopark that covers about 124 square miles of these colorful hills. Those colors are not a surface trick. They come from sedimentary layers laid down and compacted over long spans, described as deposits building up over more than 24 million years. Once the layers existed, different minerals left different tones in the rock. So the rainbow effect is really chemistry recorded in bands rather than paint on a hillside. Then the land was slowly lifted and tilted, turning what used to be horizontal layers into slanted pages that could finally be read from the outside. After that shift, the sculpting took over. Wind, rain, and weathering shaving the soft rock into ridges, gullies, and sharp edges that expose the layers with clean lines. That is why the scene can look unreal. The stripes feel deliberate, yet every band is simply a different layer being revealed as erosion removes what used to hide it. As a proof point of its geological value, UNESCO lists Zhangye as a UNESCO Global Geopark, highlighting its colorful hills and typical Dangxia landforms among its key geoheritage. The hidden part is timing and exposure. Flat light can mute the bands, while angled light makes them snap into focus, and protection measures keep most of the fragile surfaces from being walked on. Taken as a geological clue, Zhangye Dangxia is Earth showing its method in plain sight. Layers built, lifted, and patiently carved until time turns buried history into visible color. Ferrier geothermal area at the Namaskard Pass below Namafjall is a bare field of steaming vents and boiling mud pits that makes the ground look freshly opened by heat. It sits near Lake Mývatn along Iceland's Ring Road, about 4 miles east of Reykjavik, so the scene arrives suddenly, steam rising from terrain that otherwise looks quiet and ordinary. That first impression is as much smell as sight, because geothermal gases such as hydrogen sulfide give the air a sharp, sulfur-like bite that lingers in the wind. Underneath, the mechanism is straightforward but powerful. Magma heats groundwater, and the resulting steam and gases push upward through cracks in the crust, turning the surface into a vented system. As that hot, mineral-rich activity continues, the ground itself is chemically altered, and thick deposits, often described as silica, gypsum, and sulfur, coat and stain the surface. Those coatings help explain why the landscape looks painted in ochres and yellows, because the color is not decoration. It is mineral evidence left behind by heat and gas. The mud pots fit the same story. Water and fine sediments churn together, then bubble and pop as heat and gas escape, so the terrain appears alive even when the air is still. This is also where the hidden claws becomes physical danger, since the crust can be thin and unstable near vents, and multiple safety guides warn against stepping off marked paths because severe burns are possible. Even the setting reinforces the idea of a secret, because the area sits around 1,345 feet above sea level, where weather can change quickly and steam can erase clear visibility without warning. Taken as a moment of Earth's hidden geology, Ferrier is the planet briefly showing its internal plumbing in plain sight. Heat rising, rock transforming, and pressure finding release through the smallest openings. Diamond Beach is a black sand shoreline where chunks of glacier ice lie scattered like broken glass, turning ordinary surf into something that looks staged for a museum. Just inland sits Geological Glacier Lagoon, and the beach exists because that lagoon is an active exit route. Ice breaks away upstream, drifts outward, and keeps feeding the coast. Those pieces begin as calved ice from Geological, enter the lagoon, slip under the bridge to the sea, and then the ocean's timing decides which fragments return to shore. That back and forth is the mechanism that makes the diamonds, because wind and waves polish the ice as it tumbles, sharpening edges, clearing surfaces, and changing shapes with every cycle. The dark sand is part of the contrast, formed from eroded volcanic material such as basalt, so the ice reads brighter, cleaner, and almost lit from within. Even the scale behind the scene is larger than it looks, since Geological is reported to reach about 932 feet deep, which hints at how much ice and water this system can move. The hidden clause is that nothing here stays the same. The size, quantity, and appearance of the ice on the sand can change from day to day, because tides and conditions keep rewriting the shoreline. That constant rewrite is why the beach can feel like a secret being revealed and erased. 1 hour full of crystal shards, Another hour nearly empty, with the story carried back out to sea. It also explains why caution belongs in the scene, because the Atlantic surf and cold water make the edge unpredictable, and safe viewing depends on respecting the waves rather than treating the ice as a harmless photo prop. In the end, Diamond Beach is not just a beautiful contrast, it is a working conveyor belt where glacier ice becomes ocean debris, then returns briefly to land, showing in plain view how ice and water trade places over time. How does a high Andean hillside end up carved into a bright mosaic of salt terraces, so geometric it looks designed rather than naturally deposited? Near Maras, in Peru's Sacred Valley, about 30 miles from Cusco, at roughly 10,500 feet above sea level, the terraces sit far from any coastline that could explain the salt. That distance is the first clue, because the source is salt-rich spring water rising from underground, carrying dissolved minerals that were stored in the rock long before the surface was shaped. Instead of letting that brine spill away, people guide it into narrow channels that slow it down and distribute it evenly across many shallow pans. From there, the mechanism becomes simple and relentless. Thin water spreads out, dry air and sun remove it, and concentration rises until minerals can no longer stay dissolved. As the water thins, salt begins to crystallize along the pan floors and edges, turning clear brine into a white crust that can be collected without digging into the hillside. What makes the landscape feel built is repetition, because each refill and each dry down adds another layer, gradually sharpening the rims and keeping the terraces defined. That same repetition creates the patchwork look, since some pans are newly filled, others are mid-evaporation, and others are ready for harvest, all visible at the same time. Weather becomes the hidden lever controlling the pace, because rain can dilute the brine and soften the whiteness, while dry stretches tighten the contrast and accelerate the cycle. So the terrace pattern answers the question cleanly. Geology supplies the briny water, gravity and channels organize it, evaporation turns it into crystals, and steady harvesting keeps the system alive, season after season. Skaftafell Ice Cave. What kind of force can turn solid glacier ice into a hollow blue chamber, while the surface still looks calm and sealed? Skaftafell Ice Cave forms in southeast Iceland within the Vatnajökull glacier region, an ice cap spanning about 3,200 square miles, so the real work can happen out of sight. That scale matters because a glacier this large is not a block of ice. It is a slow-moving system with internal pathways that open and close over time. Seasonal thaw sends meltwater across the surface, and the water doesn't stay on top. It slips into hairline cracks and sink points and disappears into the darker layers below. Inside the ice, that same melt becomes a cutting tool, using steady flow and pressure to carve channels that widen into a chamber from within rather than from the outside. As the passage grows, the moving water scours away cloudier snow ice and leaves behind denser, cleaner ice that can hold smoother walls and sharper contours. That cleaner ice also explains the signature blue because it filters light so the chamber reads as deep color, an optical result of purity and thickness, not decoration. The catch is stability. The glacier keeps creeping and settling, so a roof that looks strong can weaken quickly as temperatures shift and internal flow changes course. For that reason, local guidance typically treats the cave as seasonal and condition-based, often restricted to winter months such as November through March, and approached through trained glacier guides rather than a permanent path. Taken as a geological clue, Skaftafell shows how Earth builds hidden spaces with melt, pressure, temperature swings, and time, then quietly reshapes or erases them again. Fingal's Cave. A cathedral-shaped sea cave lined with black organ pipe columns can look engineered, yet the only builders here are volcanic heat, slow cooling, and the Atlantic. Fingal's Cave lies on the uninhabited island of Staffa in Scotland's Inner Hebrides, where the sound of surf can echo inside the rock like an instrument. Its structure begins with basalt lava. As it cooled and contracted, it fractured into tightly packed, mostly hexagonal columns that form an orderly wall of stone. Those column seams became natural fault lines, so waves repeatedly drove into the joints, widening them over time until a long chamber opened along lines the lava had already set. The scale is part of the experience, often described as about 250 feet deep, with an arched roof rising roughly 70 feet. So spray and echo turn geology into atmosphere. Access stays conditional because the floor is sea-filled. The landing can be rough, and wet basalt can turn a simple step into a slip. So calm water decides the visit. Staffa is managed as a protected site by the National Trust for Scotland, which helps keep the cave's exposed columns and shoreline intact while people come to see it. In one clean sequence, Fingal's Cave shows how nature can write a geometric pattern into rock, then let the sea patiently hollow it into a space that feels built for sound. Zhangjiajie National Forest Park is defined by thousands of narrow, quartz sandstone pillars across the Wuling Yuan landscape, with many standing over 650 feet above the valleys. That scale is the first clue, because it points to a slow process repeated across an entire region rather than a single unusual formation. The rock here is cut by natural joints and fractures, and those weak lines become the paths where weather can begin separating solid stone into distinct blocks. Rainwater works into those cracks, temperature swings widen them, and runoff carries loosened material away, so the landscape is shaped by steady removal rather than sudden collapse. As softer sections break down faster, the harder cores remain standing, leaving behind isolated columns and thin walls that look like towers, even without any dramatic atmosphere. Over time, valleys deepen around them, and the contrast between vertical pillars and carved channels becomes sharper, making the terrain feel structured and almost architectural. The hidden clause is that this finished look is only a snapshot, because the pillars keep cracking, shedding grains, and changing shape in slow motion as erosion continues. Taken together, Zhangjiajie shows how fractures, water, weather, and time can transform one continuous mass into thousands of separate towers, proof that patient processes can produce forms that feel sudden. Preikestolen is a steep granite cliff above Lysefjord, rising about 1,982 feet from the waterline to a nearly flat rock platform. That platform is roughly 82 by 82 feet, which is why the top reads like a clean surface rather than a broken ridge. The reason it looks so sharply cut is Ice Age mechanics. During the last glacial period, ice reached this edge and water repeatedly froze inside fractures, forcing the rock apart along natural weaknesses. As blocks broke loose, the glacier carried debris away, leaving behind an angular, squared-off remnant where surrounding material had been removed. With the softer or more fractured sections stripped out first, the remaining slab became the pulpit, a leftover piece that still holds its geometry because it resisted the same breakup. Even now, a deep crack across the plateau hints at the forces that shaped it, while geological investigations have repeatedly assessed stability as safe in the foreseeable future. The hidden story is scale and patience. The cliff looks like a single dramatic moment, but it is really the cumulative result of freezing water, stress, and removal repeating over thousands of years. In the language of hidden geology, Preikestolen is what happens when ice doesn't just carve valleys. It also edits the bedrock into clean forms that feel designed, simply by breaking and subtracting what could not hold. Kelimutu's summit holds 3 crater lakes that can shift colors over time, even though they sit side by side in the same volcanic bowl. The whole system sits at about 5,377 feet above sea level, which matters because the lakes are perched directly on an active, gas-fed landscape rather than a quiet mountain basin. What drives the changes is what cannot be seen from the rim. Volcanic vents on the lake floors release gases into the water, and that input can rise or fall as the volcano's internal circulation changes. As those gases bubble up, they can stir the water from below, pulling mineral-rich water upward while rainfall refreshes the surface. So the lakes are constantly being mixed in different ways. When the mix shifts, the water's chemistry shifts with it. How acidic it is, how much oxygen is available, and that changes how dissolved metals, especially iron-related compounds, show up to the eye. Because each lake connects to the venting a little differently, the colors can change independently, which is why the trio can look mismatched rather than synchronized. That is the hidden part. The crater shapes feel stable, but the active ingredients, gas flow, mixing, and chemistry, can rewrite the surface color without warning or drama. And this is not just a historical volcano either. Records list the most recent eruption in 1968, a reminder that heat and gas are still part of the story beneath the lakes. So Kelimutu reads as a living demonstration of volcanic plumbing. Deep gases feed the water changes its chemistry, and the surface translates those invisible shifts into color that never fully settles. The marble caves are a complex of marble caverns, arches, and pillars carved directly into the shoreline of Lake General Carrera in Chilean Patagonia. That setting matters because Lake General Carrera is enormous, about 714 square miles, so wind-driven waves can keep working the same rock face again and again. The rock itself began as limestone that was slowly changed by heat and pressure into marble, leaving a calcium carbonate stone that can be worn down at the waterline. Once the lake filled the basin, water carrying dissolved carbon dioxide behaved like a mild acid, so it could slowly dissolve the marble while waves supplied the physical abrasion. That combined action targets weak points first, tiny cracks, seams, and joints, so each surge pushes farther in, widening openings that were already pre-marked in the stone. As the openings widen, the shoreline begins to undercut into chambers and corridors, and repeated water level shifts help shape pillars and arches at the heights where water returns most often. Many descriptions summarize the result as the product of more than 6,000 years of lake erosion, which fits the slow, cumulative feel of the carving. The famous blue glow inside is not a paint effect. It comes largely from the lake's turquoise water reflecting and tinting the pale marble walls with blue light. Because the formations are both striking and fragile, official tourism guidance notes they have been protected as a national monument since 1994. In the simplest terms, the marble caves are what happens when transformed stone meets persistent water. A long, quiet cutting process that turns a shoreline into something that feels built, even though it was only shaped. Geological is best known as a volcano capped by a glacier, so an eruption can begin under ice, where heat meets meltwater before it ever reaches open air. That overlap is the mechanism, because magma does not just rise, it melts ice into water, and that water can flash into steam right at the vent, multiplying force in a confined space. Steam expansion helps shred magma into extremely fine ash, which is why glacier-covered eruptions can turn more explosive than a similar volcano without ice overhead. In 2010, that magma-ice interaction produced a major ash plume that stayed suspended and traveled far, turning a local eruption into a continental-scale disruption. The risk was not just visual, because volcanic ash is abrasive rock and glass particles, and aviation authorities treated the plume as hazardous enough to trigger widespread flight restrictions across Europe. On the ground, rapid melting can also drive sudden outburst floods, and reports describe evacuations on the order of hundreds of people in areas threatened by meltwater. Only after that change starts does the scale come into view, with the volcano's summit reaching about 5,417 feet, still largely hidden beneath ice when viewed from a distance. Taken together, Geological is a clear case of hidden geology becoming visible. Ice turns heat into water, water into steam, steam into ash, and the effects can travel far beyond the mountain. In southwestern Bolivia, Salar de Uyuni spreads across about 4,086 square miles, making it the world's largest salt flat by area. It sits at roughly 11,995 feet on the Altiplano, so the White Desert is really a high, cold basin where water has nowhere to drain away. Over tens of thousands of years, ancient lakes repeatedly expanded and then dried out here, and each retreat left dissolved minerals behind, until a thick salt crust became the new ground. That crust can look motionless, but it is an active record of evaporation. Sun and wind pull water upward, salts crystallize at the surface, and the flat slowly refreshes itself as conditions swing between wet and dry. During the rainy season, a thin sheet of water can spread across the salt and turn the entire plain into a mirror-like surface. Because the ground is so uniformly flat that reflections hold instead of breaking into ripples. That same uniformity is why space agencies have used the solar as a practical reference surface for satellite instruments. It is a rare place where geology produces a clean, bright, consistent target on a planetary scale. In northern Norway, the aurora borealis is what happens when charged particles from the sun are guided toward the pole by Earth's magnetic field, and the sky starts responding. When those particles collide with oxygen and nitrogen high above the ground, the upper atmosphere releases light, forming curtains and arcs that can ripple and rearrange in real time. NASA notes the familiar green glow tends to form roughly between 60 and 120 miles up, while red appears above about 120 miles, so color is quietly telling you altitude. That height is why the display can feel close while remaining untouchable. The stage is far above fjords, roads, and rooftops, in thin air where collisions can shine. For Norway, the practical window is the dark season, with official travel guidance noting northern lights can be seen from late September through late March, when nights are long and dark. Even in the right season, it comes down to alignment. Enough solar activity to send a stronger stream of particles, and a clear, dark sky that does not wash the glow out. On stronger nights, the activity spreads and the patterns intensify, which is why the same location can look quiet for days and then suddenly fill with fast-moving bands. Seen this way, the northern lights are less a mystery show than a readable mechanism, space weather made visible, turning invisible magnetic forces into light the human eye can follow. Deep inside Mexico's Nica mine, a sealed chamber holds giant gypsum crystals, so large they feel architectural rather than natural. Some of the crystal beams reach about 36 feet long, and the cave's heat can sit around 136 degrees Fahrenheit, with humidity so high the air stops being forgiving. Those extremes are not decoration. They are the growth conditions, because the crystals formed underwater in mineral-rich groundwater that stayed warm and unusually stable for long stretches of time. At that narrow, sweet spot, dissolved minerals could slowly reorganize into gypsum, allowing crystals to keep growing instead of forming small, cloudy grains that stall out early. What makes the cave feel like a geological secret is that it only becomes visible when the mine's water level drops. Yet exposure to air and heat threatens the very surfaces that water protected. So NICA is a clean mechanism in one room. Steady heat plus mineral water plus time can build crystals on a human scale. But the same conditions also make the place difficult to enter and rarely seen up close.